drawing Lewis structures is something that needs quite a bit of practice. And even then, while you can draw using common sense Lewis structures for 99.999% of covalent species, as we'll talk about in the first year of the main course, there are quite a few species for which you cannot draw Lewis structures just following common sense. But we won't worry about that too much now. What we will worry about, though, is going a little bit more deeply into the whole concept of two atoms coming close together such that they can share electrons. So let's just take it nice and simply to start off with to get the concept across. Two hydrogen atoms that are going to move closely together. Okay, now if we plot out a little energy curve where along the horizontal we have the distance between the hydrogen atoms, and up here we have the energy. So over here, right, long hydrogen distance, those two hydrogen atoms were completely unaware of the other one's existence. As you start bringing them closer together, though, one hydrogen nucleus can start to see and attract to the electron of another one, and that's good. So that decreases the energy a little bit, and then as they get closer and closer, they really start feeling each other. But as they start getting even more closely to each other, the hydrogen nuclei can start to feel each other. So now you have two opposite effects. You have a good effect, the hydrogen nucleus of one electron being attracted to the electron of the other hydrogen atom, but then the two hydrogen nuclei repelling each other, which is a bad thing. And so you reach a minimum here at which the best position of closeness for the nuclei attracting to the electrons and closeness the nuclei repelling, and then as you get closer still, repulsion takes over as the dominant feature, and the energy situation shoots up. So the point of this is that there is a minimum energy that corresponds to a particular optimal hydrogen-hydrogen distance. We call that distance the bond length, and we'll talk more about that in a second. And we talked about that optimal energy, the energy that is given out, the energy that stabilizes from having a zero energy where the hydrogens are doing nothing to where they're forming the bond. Now, first of all, start talking about bond lengths, and we define that optimal bond length, that distance between the atoms when everything is perfect, as being the sum of the two atomic radii. Remember, we talked in our periodic properties video about atomic radii, and I said that, well, one way you can get atomic radii is you look at the distance between the atoms in the element and you divide by 2. Another way you can get it is you can look at the bond length in covalent molecules in which the atoms are different from each other, and the sum of the radii is equal to that bond length, is equal to the distance between the two nuclei. Now we can look at various measured bond lengths. So XY, just the two atoms, bond length in picometers, so carbon hydrogen, 109 picometers, carbon chlorine 177. Carbon chlorine bond much bigger than a carbon hydrogen bond because a chlorine atom is bigger than a hydrogen atom. And then remember, as you go down a group, so chlorine, bromine, iodine, the atoms get bigger, so the bond lengths get bigger. And so a general trend, the bigger the atoms, the longer the bond. Again, next year we'll talk about some exceptions to that, some other considerations you have to worry about. We also talked about single, double, and triple bond. Now, single bonds are where two atoms are held together by 2 electrons, double, where 2 atoms are held together by 4 electrons, and triple, where 2 atoms are held together by 6 electrons. It should make sense, I hope, that the more electrons there are holding those atoms together, the more they're held together, the more closely they can get to each other, and so the shorter the bond. So single bonds are longer than double bonds are longer than triple bonds. Turning to the bond energy, or the bond strengths. The bond strength is defined as being the energy that has to be put in to take 2 atoms that are quite happily bonded together and break them apart. Seeing as how that bond putting them together, sticking them together. You have the attraction of the nuclei from one atom to the electron from the other atom. You have to put energy in to pull those apart. And as we'll talk about later on in the course, putting energy in means that it's actually a bad situation. You've got to put energy into things. Energy would far rather be lost. And that is another way that we can express the bond energy. We can do it in terms of what we just looked at there, taking two atoms that are separately from each other, bringing them close enough to each other so that you've got that best energy situation, and that's energy being given out as they go from the lone atoms to the bond there. Don't have to worry too much about this for now. Just know that we will be addressing this next semester. It is worth looking at some values of this bond energy. So again, general trend in general, the longer the bond, the weaker the bond, because the further away that the atoms are from each other, the less attraction there is of the nucleus to one for the electrons of another. And so you can see, if you remember, that as we went down, for example, this first column, the bond length, as we go from CH to CCl to CBr to Ci, the bond length increases, the bond energy decreases. There are definitely some exceptions to that rule. There are some factors, other factors we have to think about that we won't worry about too much now. Similarly, as we look at single bonds to double bonds to triple bonds 6 electrons, double bonds 4 electrons, single bonds 2 electrons, you should obviously appreciate that it's going to take more energy to pull 6 electrons worth of sharing apart compared to 2 electrons worth of sharing. So single bonds are always weaker than double bonds are always weaker than triple bonds. A last extremely important concept when we are thinking about bonding is electronegativity. Electronegativity is a measure of the extent to which an atom desires electrons in a shared bond. Okay, we've been talking about this sharing being the way that atoms will increase their number of electrons, and anytime we say sharing, the automatic assumption is that it is equal sharing. However, things that should be shared equally rarely are. The example I'll always use for this is the concept of an aeroplane seat arm, that armrest in between two seats that should, of course, be shared equally by the people there on either side. Never is the case. When we fly, typically I sit in the aisle, my wife sits by the window, and our son sits in the middle. He is much more electronegative than we are because he gets far more of a share of that armrest. His arms pretty much occupy 99% of the armrest. My wife and I get about 1%, a little sliver of that armrest for ourselves. He's more electronegative than we are because he desires that shared armrest more than we do. Generally, we say if Y is more electronegative than X, in other words, Y wants electrons more, right? Y pulls those electrons more to it than average. And that unequal now sharing of those electrons means that there is now a partial ionic character. The more electronegative atom gets a larger share of something negative, so it's a little bit more negative. The less electronegative atom gets a little bit more positive, right? It doesn't have the share of electrons that it should be. If we look at the periodic table, its electronegativity is a periodic property. As you go from left to right, it increases. As you go up, it increases. Okay, some values here, and we'll talk next year about where these values particularly come from. So you can see fluorine, 3.98 is the most electronegative atom, then oxygen, then chlorine, then nitrogen, then bromine, and so on. Okay, no electronegativity for now for the noble gases because, of course, they're happy. They don't want to form bonds. We'll talk later on about molecules formed by the noble gases, but that just comes because of other atoms being really weird rather than noble gases wanting to get happy. So we'll say no electronegativity associated with noble gases because they don't make bonds. Electronegative associated with all other ones. The closer you are to fluorine, the more electronegative an atom is. If we just think about, say, hydrogen chlorine, this pink Oval represents the electron density that would be there if it was a nice equal sharing of electrons. However, chlorine has an electronegativity of 3.16, hydrogen 2.20. Chlorine is more electronegative than hydrogen, and so therefore it has more of a share of electron density than hydrogen does, as illustrated by a deeper pinky, orangey red over by the chlorine, much lighter one by the hydrogen. The chlorine has more of a share of those negative electrons than it should be, so we say it's a little bit negative. The hydrogen has less of a share than it should, so we say it is a little bit positive. And overall, we say that this bond is a polar bond because the two ends are different from each other. Now that we've introduced electronegativity, we can finish off our discussion of bonding by pointing out that it is not as black and white or ionic and covalent as we might have possibly implied in our discussion. We've said metals and non-metals make ionic bonds, non-metals and non-metals make covalent bonds. But as you've seen, those polar covalent bonds, if they're between atoms of different electronegativities, will have an unequal sharing of the electrons, which means that one end starts to become negative, the other end starts to become positive. And as that electronegativity difference increases, so does that extent of negativity and positivity. Start off by examining some bonds to fluorine, fluorine being the most electronegative atom. We start off with the bond between fluorine and fluorine, then oxygen fluorine, nitrogen fluorine, carbon fluorine, hydrogen fluorine, boron fluorine. Even though boron is depicted here, it is less electronegative than hydrogen. And then beryllium to fluorine, lithium, sodium, potassium, and cesium to fluorine. Okay, we would say that a fluorine-fluorine bond is covalent. They're sharing electrons and it's going to be non-polar. We would say a cesium-fluorine bond, at this point cesium fluoride bond, would be almost 100% ionic. That electron would get transferred from the cesium to the fluoride, and the positives and the negatives would interact. In the middle here, we would have polar covalent, and we would have just regular old ionic. And then somewhere in between those meet. Where does it go from polar covalent up to ionic? Where do we stop saying they're sharing, and when do we start saying that they are transferred? And that is something that just, if it comes up, you'll have to just think your way through. Okay, good indicator comes from looking at the difference. This delta here means the difference in electronegativity. Fluorine, of course, both fluorines 3.98, so the electronegativity is 0, and I'm rounding here. Okay, as we go along here, the electronegativity difference increases. We go 0.6 for the oxygen to the fluorine, 1.4 or so for the carbon to the fluorine, 2 from the boron to the fluorine, 3 from the lithium to the fluorine, and so on. Okay, as you go further along, this continuum from covalent to ionic, we can indicate it by the difference in electronegativity. Generally, people would say that electronegativity difference of about 2 would be it, but a boron-fluorine bond is very definitely, a covalent bond, just a very polar covalent bond. I'm not going to ask you to say for sure, hey, this is a covalent, this is an ionic bond, when it's sort of in the middle. I would expect you to say that sort of bonds formed between atoms down in this region are covalent. Bonds formed between metals and non-metals we're going to be thinking of mostly ionic. Hope that wasn't too confusing a way to finish things off. Hope you enjoyed it, and we'll be back to talk about how we can use Lewis structures to predict the actual three-dimensional shape of molecules.